Hey everyone, I'm Nick and welcome to another episode of This Week in Architecture. And so today we're going to continue on with looking at a recent paper that came out of ASPLOS 2019. ASPLOS, the conference, is coming up in just a few weeks. And so I figured that we'd talk about this. So ASPLOS, if you're not familiar, stands for Architectural Support for Programming Languages and Operating Systems. So it's one of the upper conferences that people in architecture, as well as some other fields, want to submit to. And so we're going to talk with this one that came out of UC Riverside, San Jose State, and Tesla. The only reason why Tesla is on this paper is because one of the postdocs that was on this paper, he left and he ended up going and working for Tesla. So Tesla gets on the paper. So let's talk about this paper now. And so here we have the actual paper. And so let's present and full screen. All right, so let's give an overview. So what is the paper on? So one of the claims they make is that the register file substantially affects performance and energy efficiency. So every single application is going to be loading things into the register file, reading from the register file, writing to the register file, etc. So the register file, if you're unfamiliar, when you load in values or when you're working with data, your data gets loaded into the register file, and then inside of the pipeline, when someone, say, wants to do, A plus B, A will say be in a register entry, B will be in a register entry, so you'll load out of the register file. But what's the problem here? So GPUs have tons of threads, so how do you deal with port contention on operand collectors and register file banks? So operand collectors are these things inside of the GPU architecture that schedule reads and writes to the register file in a way to prevent bank conflicts. And then the register file itself is banked, which means that it's mapped in such a way to also help prevent multiple threads from trying to access the same bank at the same time. But you can't get rid of all bank conflicts. You're going to run into cases where maybe it's even pathological, where tons of threads are trying to access. They all they're all knocking on the same operand collectors, and then they all end up hitting the same register file banks. So they want to address this, and they want to address this using this idea of CORF, which is a coalescing operand register file. And we'll talk about what that is in a second. But the key idea is they want to combine reads to multiple registers for a single instruction into a single read. So what exactly does this mean? So if we can read out two registers worth of data in only one read, then in the ideal case, if say every single access can be coalesced, or for every single instruction that has say like two operands, then we're basically cutting down half the traffic. Now, of course, that's kind of in the limit, but they kind of motivate that there's a lot of opportunities to do this coalescing. So let's talk about the technique. So the main idea is they're going to use the compiler in order to kind of mark register pairs that are accessed frequently together. And then those should be put into the same physical register entry. So let's take a look at this graph that they make. So the edge weights kind of represent how many times these two registers are referenced together. So in this case, R1 and R3 are referenced 10 times together. So they're both on the right side of an assembly instruction together as operands. R2 and R4 7 times, and R1 and R2 8 times. So what ends up happening is, even though that R1 and R3 is the highest edge weight, which means that they're referenced the most together, turns out R3 is just kind of a big value and it needs its own register. But R2 and R4 are smaller values, so they go ahead and put those two together. So maybe those are both 16-bit values, so they can fit in a 32-bit register file entry, or 32-bit register. And then R1, because it's very small, they kind of just throw it off into its own register, so it can be co-located with a bigger say a bigger value. Maybe if this is 32 bits, maybe you could have some 24-bit value in here, or just throw in something more reasonable like a 16-bit value. That makes more sense. So again, this has to be compatible narrow width values, so both 16 bits. It can't be a 16-bit one and a 32-bit one. And then of course they try to pack the highest frequency pairs together. So how do they what is the kind of limitations of this? So one thing we see right off the bat is that, okay, so when they read out R2 and R4, which happen quite a bit, they only have to do one read in order to get these two register values. Now, that's good, but what about the fact that R1 and R2 are also used fairly frequently together? How do we exploit that? Because in this case, we don't exploit that at all. We just kind of lose that. They have to be in the same physical register entry. So that's what they do with CORF++. And so the idea is to coalesce multiple physical register entries. And they use this register affinity graph to find some commonly paired operands. So this is this graph coloring kind of problem. So, it's important to know that, when they're doing this, this graph coloring and, deciding which registers will be aligned to which side of the register file, it falls into something called a bipartite edge frustration problem. And so this turns out to be a very hard problem to solve. So they don't guarantee that this is an optimal solution, but they do guarantee that it works pretty well. So it's guided based upon some heuristics. So they have this register affinity graph that says how often registers you use together. And what they do is they try to alternate in between. So that's what these colors represent. The colors represent these left aligned, and or what they want these to be is how these are going to align inside of the register file. And the reason why I say align and what I actually mean there is that in the register file itself, they're going to have two paths to go down. So you can read off things that are in the left side of the register file or the right side of the register file. That way, they don't need to be in the same physical entry. They just need to be either on kind of left aligned or right aligned. And so what they want to do is they want to take the highest edge weight things and they want to put them on opposite sides. That way they're maximizing the number of chances they get to coalesce. And we'll see that example in just a second. So this is down there in the bottom left. That's kind of this dual address data register file. So the the lookup into the register file comes in. It gets split down into two data paths, and they see which values they're going to read out down here. And they use some muxes in order to, which are multiplexers, which just kind of make decisions based upon inputs, and they decide, who they're going to read out. Okay, so let's look at an example. So here we have some SAS code, which is just the machine ISA or instruction set for NVIDIA GPUs. So it starts out with some loads, so a global load and then a substitution. So up here they have their compiler marking. So their compiler marking of whether something is going to be left aligned or right aligned. So over here, R1 doesn't have any. It doesn't have any entry in here, which means it just says use this first fit policy. That's what's default. And so if it has a first fit policy, it just finds the first space, right? So it goes into this physical entry 0. Right, but the second one, the substitution that writes into R2, well, that does have a mapping up here, and it says R2 should be right aligned. So it finds the first right aligned register. Then we go over here, this shift right is also right aligned, so it finds the next available entry and makes it right aligned. Then we do another load into R3, and R3 is left aligned, so it gets loaded into the left side of this first register in P0. Then we get to the first kind of interesting one. So here we have an add, and it's going to R5 is left aligned, so it's going to store the value into this left aligned register down at P2. And then we see in this blue box R2 and R3. That means these things can be coalesced. So R2 is on the right-hand side, R3 is on the left-hand side. So with that kind of dual address data path, they can read out both sides at the same time, even though they're in different physical registers. And then over here with this multiplication and the subtraction, the same thing happens. So they overwrite R1 and they overwrite R2. So there's no real change or update to the register file in terms of mapping. But R4 and R5, which are on different sides of the register file, and but in the same physical register entry, they get coalesced. And then R3 and R4, which are on different sides of the register file, but in the and in different physical register entries, they get coalesced as well. All right, so let's look at some results. So they find that in the benchmarks that they look at, there's a quite amount of coalescing opportunities, and it turns out that CORF++, it can get quite a few of them. So CORF does an okay job. First fit is just if they, it's just a naive packing, so it has no idea of this register affinity graph. So CORF does an okay job, just about as good as first fit in a lot of cases, sometimes better. And then the upper bound, CORF++ and the upper bound are decently close in some cases. But as we can see here, they still get about 60%, or on average, more like 50% of the total, the upper bound of coalescing opportunities. So over here, they show the number of reduction in register file accesses. And so CORF++, a little over 20% of the accesses or accesses to the register file can be reduced. And then it leads to an IPC improvement of about 9%, which we see over here. And then it turns out, because we're packing things into the register file, we don't need quite as many registers because, we're really utilizing this space better. And this technique can also be used with another paper we'll talk about another time from 2015 called Register File Virtualization. And another interesting thing that they say in the paper is that their technique is complementary, which means that they can use it with register file virtualization as well. So this is their overall results. So we'll just look at their main result. So they get a better performance, so about 9%. They can decrease register reads by an average 23%. And then they decrease register file dynamic energy by about 17%. And of course, because they can also use register file virtualization, they can decrease the size of the register file by 43%, right? And maintain the same performance. So what are the key kind of things? Let's talk about kind of conclusions. So its complementary ideas are good. So the fact that this can be added on to previous work in the area is a very good thing. It means that, if you do completely disjoint work that doesn't kind of build on other people's work or work with other people's work, it makes it really hard to integrate ideas. So that's always a good thing if ideas are complementary. But so a couple things that I did notice in the paper. So if we go back to the results. So this is 9% performance improvement in a simulator. Simulators are inherently going to have, some amount of error associated with them. They're not perfect. They're not perfect models of hardware. So 9%, you're starting to get into the margin of error. It's, maybe just above it, but it's still fairly low as far as improvement goes. Register reads is pretty significant, 23%. So that's a good metric to have. And another thing to kind of keep in perspective is this register file dynamic energy. So it's about 17%. But it's important to notice that this is just the dynamic energy for the register file. This isn't for the entire GPU, the total system dynamic energy for the GPU. And so we saw in Gebhardt's paper from the 2011 ISCA, the register file cache, the register file itself only amounted to about 3.3 watts of total system power. So to put it in perspective, 17% of that being saved, it's still a fairly low number. All right. So that's going to do it for today. Again, this is going to be, this CORF coalescing operand register file for GPUs to appear at ASPLOS 2019. As always, feel free to go to my GitHub page at github.com/coffeebeforearch. I've got code for all the other series that I do, as well as if we go here to Coffee Before Arch and then This Week in Architecture repository, I've got links to all the other papers that we've done, as well as all the slides we have. So we looked at this paper CORF this time, register file cache last time, and then we also have the slides, right? So like these are the slides that we used last time for the register file cache. So feel free to check this out. Let me know if you have any questions or if there's a specific paper in this area that you would like to go over, and I'd be more than happy to present it. Right, again, Nick from Coffee Before Arch, and I hope you have a nice day.